In this video, we are going to look at the Henderson Hasselbalch equation and figuring out the pH of buffer solutions. We're just going to bring up the document for that. Looks like we have it here. A little pointer here. Okay, I think we're ready to go. So the Henderson Hasselbalch equation right here, pH equals pKa plus log of the base over the acid, is often used with buffer solutions. Remember, buffer solutions are resistant to changes in pH. If you have a system and you add H plus to it, the pH will go down, but it won't go down as much if that system is buffered. It will minimize the effect on pH. If you have a buffer solution, you add OH minus, it's going to raise the pH, but not as much as expected. Again, it minimizes that pH going up. So let's look at this equation. pH equals pKa plus the log of the base over the acid, which is also pH equals, what is pKa? It's the negative log of Ka, just like pH is the negative log of H plus, and then the log of the base over the acid. Now, buffer systems have a weak acid and its conjugate base. And the reason they don't get affected much by changes in acid or base is because it contains both an acid and a base component. So if you had a strong acid, this part of it, the base, converts the strong acid to a weak acid, lessening the effects on pH. If you had a strong base, this extra acid converts part of that strong base to weak base, again, lessening the effects on the pH. As long as the amount of acid or base you add is less than the amounts of the weak acid and weak base present in the system, you won't have a big impact on pH. Here's how the calculations end up working. Let's see. So we are going to take acetic acid, and that breaks up into H plus and its conjugate base, the acetate ion. And let's say we have equal molarity of the acetic acid and its conjugate base. We'll plug that into the Henderson Hasselbalch equation, and it says pH equals the negative log of 1.8 times 10 to the negative fifth, which is a pKa, plus the log of 0.10 over 0.10. And when I do that, I get 4.74. And then because the acid and base is the same, the log of 1 is 0, so I get a pH of 4.74. Let's say I have twice as much base than acid. I'm just going to scroll this down a little bit. I'm sorry, twice as much acid as base. So the molarity of the acid is twice as big as the molarity of the base. And I still plug in the equation, pH equals the negative log of, and I put the base over the acid, so I put 0.10 over 0.20. It ends up being negative 0.30. So my final pH is 4.44. So even though I had twice as much base than acid, I still didn't change the pH that much. It was only a 0.3 change. Notice because I had more acid than base, the pH actually went down a little bit. Okay, let's look at the other situation where I have twice as much base than acid. And if I plug that in, I get pH equals the negative log of 1.8 times 10 to the negative fifth, which is 4.74, plus the log of 0.2 over 0.1, which is plus 0.30. So my pH goes up to 5.04. Notice compared to 4.74, I have more base than acid, so it makes the pH go up, but not by that big of amount, even though I had twice as much. Now, what's nice about this formula, it works for when you have concentration of base and acid. Okay, it also works just comparing moles. So you don't have to necessarily get things in molarity. You can just look at the moles and do a comparison with that. Let's just look at a hypothetical thing. What if I had 10 times as much base than acid right here. Well, what's the log of 10? That's 1. So even 10 times as much base than acid will still only move the pH by a factor of 1. So buffer solutions, they are affected by pH when you add a strong acid or a strong base, but that effect is minimalized. Thanks for watching.